Hello again. In this lecture, we will learn how to find equivalent resistance. Now, we will look at two types of combinations. The first is called a series combination and the second is called parallel combination. We will identify these combinations and see the difference between them. So let's start with the series combination. So a series combination looks as shown. So in this circuit, we have a battery which creates a potential difference V, and we have two resistors, one of resistance R1, the other of resistance R2. Now, we wish to find the equivalent resistance. To do this, let's first analyze the circuit. Now, in this circuit, we see that this is the positive terminal and this is the negative terminal of the battery. So we can tell the direction of current. The current will flow out of the positive terminal and will return to the negative terminal. Now, going by these arrows, we can draw the current in the remaining branches. So, let's assume that the amount of current that flows is I. So, in this case, I amount of current flows from this battery into resistance R1. Now, if I amount of current enters R1, the same amount of current must leave R1. That is the only way that R1 will remain neutral. And when current flows, everything remains neutral. You can also think of it through Kirchhoff's current law. You can say that if this resistor is thought of as a single entity, then the amount of current that is coming in should be equal to the amount of current that leaves this resistor. Right. So I amount of current flows into this resistor and the same amount flows out of this resistor. Then that current enters the resistance R2 and the same amount I leaves the resistance R2. Please note that resistance, what it does, it offers a form of resistance to current. But that does not mean that the current which enters a resistor comes out reduced or depleted in any form. This is one of the very common misconceptions people have. They tend to think that if we have a resistor, then the amount of current that enters will be more than the current that leaves the resistor. That is not the case. Whatever amount enters the resistor is the same amount that leaves the resistor. Right. So in this circuit, what is basically happening is the entire current that enters R1 also enters R2, which means the current through the two resistors is the same. Such a combination is called a series combination. So the requirement for two resistors to be in series is that current should be same. So two resistors are said to be in series if and only if the current through the two resistors is the same. Right. Now, let's try to find the equivalent resistance. To do that, we will use Kirchhoff's voltage law. Right. So let's say we are starting from this corner, then we will go in a loop like this and finally return to the original point. Right. So during this journey, again you see from this point to this point, you are only encountering a conducting wire, and we saw that conducting wire has constant potential and hence there will be no potential difference. The first potential difference will be encountered across this resistor. Also notice that this is our direction of movement. This direction of movement is the direction in which we are moving to apply Kirchhoff's voltage law. Now, if you recall, we had seen that if your direction of movement and the direction of current are the same, the potential difference is negative. So we can write the first potential difference, which is across R1, as minus I R1. This is because the current is flowing in the same direction as the direction of our movement. Right. Then from this point onwards to somewhere till here, before the beginning of R2, we know again there is a conducting wire, hence there is no potential difference. The potential difference will be encountered when we jump across R2. So in this jump across R2, again our direction of motion and the direction of flow of current are both the same. Hence the potential difference will again be negative. So the second term is minus I into R2. And finally, we see the last difference that will encounter will be across the battery. So there are only 3 points where you will encounter potential difference. So the last difference is encountered across battery. So you see that in this jump, we are jumping from the negative to the positive terminal. So the final point is at a higher potential, and hence this difference will be positive. So this should add up to 0. Right. So if you simplify this term becomes that V is equal to IR1 plus IR2. Now you could take I common and the term becomes I into R1 plus R2. If you rearrange this, we get that V by I is equal to R1 plus R2. Now, if you think about this expression, the numerator, which is V, is basically the total potential difference applied, and the denominator, which is I, is the total current in the circuit. If you compare it to Ohm's law, we know that V by I should be equal to R. This is given by Ohm's law. So, in this case, if V is the total potential difference and I is the total current, then this value that we are getting is basically the effective or the equivalent resistance of this circuit. So, when two resistors are applied in series, that is, they have the same current flowing through them, then their equivalent resistance is simply the sum of the two resistors. Now what this means is that this given circuit can be simplified to this circuit, which is that we can have a single resistor which has resistance R1 plus R2 connected to a battery of potential difference V. And the behavior of these two circuits will be exactly the same. And this is what we mean by saying that the equivalent resistance is R1 plus R2. So whenever two resistors are in series, that is, the current through them is the same, they can both be replaced by a single resistance which has the resistance equal to the sum of their individual resistances. Right. So this is series combination, and we saw that equivalent resistance is R1 plus R2. Now, two resistance are said to be in parallel if the potential difference across them is the same. So potential difference should be the same. Right. So when can we see such a situation? Let me draw one. So if we have R1 like this and R2 like this, then if you think about it, both of them have the same potential difference, which is equal to the potential difference of the battery. How is that? Let's say this is point A. Then from this point to this point, the potential is the same. So in a way, we could say that if this point is being called A, then this point can also be called A in terms of potential. Similarly, this point can also be called point A because all three of them have the same potential. On the other side, if this point is called B, then this point can again be called B, and so can be this point. So if you think about it, both of them have a potential difference of A minus B, which is same as the potential difference across the battery. Right. Now, to find our equivalent, we will again use Kirchhoff's voltage law. But this time, we will use it twice. Let's see how. The first time, we are going in the smaller loop. And this is our direction of movement. Right. But even before that, let's mark the direction of current. To do that, we know that current will leave the positive terminal of the battery and will return to the negative terminal of the battery. So, we could say that I amount of current is leaving the positive terminal and the same amount I will return back. Now, when this I amount leaves at this junction, it will get split. So, if a small I amount of current goes into this branch, then the remaining current should go in the upward branch. That current, could I say, would be capital I minus small I, because capital I was the total amount of current that was coming to this junction. Of this capital I current, small I current left this branch. So the remaining current will move in the upward direction. Right. So if I minus I current goes here, the same current returns at this point. And if small I current enters from the left side of this resistor, the same small I leaves the resistor from the right side. You can also check that these two will again add up to form capital I current, which returns to the battery. Right. So this roughly shows the picture of how current will flow in such a circuit. Right. Now, let's get back to our Kirchhoff's loop. So this is the direction of motion. If you think about it, in this entire loop, there are only 2 points where we will encounter a change in potential. The first point is across the resistor and the second is the battery. So for the smaller loop, the first term would be for this resistance. Once again, notice that the direction of flow of current is same as the direction in which we are moving through this loop. So, we have already discussed that when such a thing happens, that the direction of movement in the Kirchhoff's loop and the direction of flow of current are the same, then the potential difference is negative. So, the first term becomes minus of the current is small I into R2. Right. Then the second term is the jump across the battery, which is from the negative terminal to the positive terminal. So the second term is positive and equal to V, and this should be equal to 0. So we get that V is equal to small I into R2. Now, Let's look at the second loop, which is the bigger loop. So we will start from this end and go like this. So this is the direction of movement along the loop. Right. So in this loop again, we see that there are only 2 points where we will encounter a potential difference. The first is a jump across AB, the resistor R1, and the last is the jump across the battery, because everywhere else there's only conducting wire. So for the second equation, we get the first term would be, again you see, direction of motion in the loop and the direction of flow of current are the same, so the potential difference is negative. So the first term becomes capital I minus small I, the current, into the resistance, which is R1, and there has to be a negative sign because the potential difference is negative, plus V is equal to 0. So this was the first equation, and from here we get the second equation, that V is equal to I minus I times R1. We want to find the equivalent resistance. Now we have already found it once, so you know that when we are trying to find the equivalent resistance, we basically wish to find an expression like V by I. So to do that, we rewrite this equation as V by R2 is equal to small I, and this can be written as V upon R1 is equal to capital I minus small I. Now add these two equations. What do you get? On adding these two, you see that V by R2 plus V by R1 is equal to capital I. So now what I'll do is take V common and take it to the right hand side. So you'll get something like 1 by R1 plus 1 by R2 is equal to I upon V. Right? You get that 1 by R1 plus 1 by R2 is equal to I upon V, which is the reciprocal of this term. So if this term is R equivalent, then can we say that I upon V is basically 1 upon R equivalent? It is, right? Because V by I is resistance, then I by V would become 1 upon resistance. And hence, we can say that in case of parallel combination, the equivalent resistance is given by 1 by R equivalent is equal to 1 by R1 plus 1 by R2. So this is the expression for R equivalent in case of parallel resistance, that 1 by R equivalent is equal to 1 by R1 plus 1 by R2. Right. If you think about it, you can rearrange that expression. We can write that 1 by R equivalent is equal to, taking LCM, you will get R1 R2, and in the numerator it will be R1 plus R2. If you flip the terms on both sides, you get the expression that R equivalent is equal to R1 R2 upon R1 plus R2. So this is another way to remember the equivalent resistance in case of parallel resistance. So to summarize, we saw that there are two types of combinations, which is series and parallel. Two resistors are said to be in series when the current through them is the same, and they are said to be in parallel when the potential difference across them is the same. And when the resistors are in series, the equivalent resistance is given by R1 plus R2. And when they are in parallel, the resistance can be given by either of the two expressions, One is that 1 by R equivalent is equal to 1 by R1 plus 1 by R2. The other form is that R equivalent is equal to R1 R2 upon R1 plus R2. This form makes it simpler to calculate, so I would suggest that you remember it in this form. Well, this brings us to the end of this session. In the next session, we will solve a few problems based on what we learned in this session.